Now to capacitor families, available capacitor families, and which families to use for a buck converter. So here I'm showing two basic families. I didn't include other capacitor like mica, oil and paper, plastic, film capacitor. Basically, I just focus on two types: multi-layer ceramic capacitors and electrolytic capacitor. So out of all these families, you will find that at the end of the day, multi-layer ceramic capacitor class 2 and 3, which in the data sheets they are indicated as X7R and X5R, the dielectric constant or the dielectric used in these class 2 and class 3 multi-layer ceramic capacitors, are indicated as X7R and X5R, so that you know these capacitors are class 2 and class 3 or multi-layer ceramic capacitors. So two families will focus on for DC to DC converters or buck converter, the multi-layer ceramic capacitor class 2 and class 3 and aluminum electrolytic capacitors. So what are the advantage and disadvantage of each? Well, let's start by the multi-layer ceramic capacitor. And we have aluminum electrolytic capacitor. So first of all, we'll find that for value, aluminum electrolytic capacitor can obtain very large values of capacitor up to 300 millifarads, while multi-layer ceramic capacitor are up to 1 millifarad. So if you need very large capacitance, a few millifarads or higher, then you should think about aluminum electrolytic. The other thing is for size and cost. You will find that multi-layer ceramic capacitors are way smaller than aluminum electrolytic capacitors, as well as much cheaper. And in terms of quality or the equivalent series resistance of the capacitor and equivalent series inductance of the capacitor, again, you will find that multi-layer ceramic capacitors are much better in terms of the equivalent series resistance and equivalent series inductance. They have much lower equivalent series resistance in comparison to aluminum electrolytic capacitor, which is something I'm going to discuss briefly in the following slides. Now, what about aluminum electrolytic capacitor? As I mentioned, they can obtain very high values. That's number one. Number two, something called voltage coefficient. Voltage coefficient of aluminum electrolytic capacitor is way smaller than multi-layer ceramic capacitors, which is a major issue. And finally, the lifetime. You will find again aluminum electrolytic capacitor lasts for a longer time. So essentially, once they are installed in the circuit, maybe they last whatever, say 20 years, while multi-layer ceramic capacitor 5-10 years. Okay. So this is how multi-layer ceramic capacitors look like. It looks like it's surface mount component basically. And there's also leaded version of this multi-layer ceramic capacitor. If we look at the surface mount, you will find there is a standard for the surface mount. So, for example, usually DJK uses the imperial code. If we have 0402 capacitors, this means essentially this capacitor is a footprint. It has two terminals, terminal 1, terminal 2, and its X dimension is about 1 millimeter. Sorry, Y dimension is 1 millimeter, while its X dimension is half a millimeter. How did I know that? Because for 0402, its dimension in metric code is 1 millimeter by 0.5 millimeter. Say 0805, this means it's 2 millimeter on this side and 1.2 millimeter on the other side. Okay, so that's the footprint that we use to design a printed circuit board and install a multi-layer ceramic capacitor in our circuit. As for aluminum electrolytic capacitor, it looks like this, which you are familiar with in 10B and 10C. Or there is a version of them as surface mount. This is like very expensive types that typically you would see inside Apple product, because as I mentioned, aluminum electrolytic capacitor, they have almost zero voltage coefficient, as well as their life is long. So if you want to build something reliable, you want to use them. Now, if you look at, this is an aluminum electrolytic capacitor. Its equivalent circuit is shown as here. That's 47 microfarad. Its ESR is 1 ohm. While for the same 47 microfarad, if you use multi-layer ceramic capacitor, you find that its ESR 2.5 milliohm. So reduction from 1 ohm all the way to 2.5 milliohm. Why is that the case? Why multi-layer ceramic capacitors are very good in obtaining very small values of ESR? Well, if we look at the construction, this is a multi-layer ceramic capacitor, and this is the side view if we look from this side. And as you can see, this is one capacitor and then stacked on another capacitor and so on. So you see, say if this is one terminal, all the capacitor with positive terminals are connected in parallel via this, say. On the other hand, all negative, the other terminal is connected in this. So essentially all the capacitors are connected in parallel. On the other hand, if we look at this, and that's something I mentioned before, aluminum electrolytic capacitor, why it has very high series resistance? Because the capacitors, this is one capacitor, another capacitor, another capacitor, is two foils that are rolled on top of each other and separated by a dielectric. So what happens is, as you roll them, if you look at the equivalent circuit, you take the ESR of, say, the top plate, and you are connecting them in series, and then eventually this is the lead, the positive lead or whatever, and then the ESR of the negative terminal, you are connect them in parallel, but they are the plates are connected in series, right? So the ESR add up, and then you take the negative terminal. On the other hand, the multi-layer ceramic capacitor, you have capacitors connected in parallel, but essentially with a very short piece of conductor as shown here, while this one is very long foil, so the ESR keep adding up. Okay, and that's why aluminum electrolytic capacitors suffer from high equivalent series resistance in comparison to multi-layer ceramic capacitor. So why in some application we prefer aluminum electrolytic capacitor? Well, it's related to what's called voltage coefficient. And what does that mean? Well, if you have a capacitor and you apply 0 volts across its terminal, you will get this capacitance at 0 volts. Now, if you take the same capacitor and apply across it 0.9 Vmax, where Vmax is the maximum voltage it can handle, or its rated voltage, you will find that at 90% or 0.9, ceramic capacitor, essentially their values decreases by up to, as you can see, 60% for this cap, and 40% for this one, more than 40% by this one cap. So essentially, you got like 100 microfarad cap. At 0, you will see 100. At 0.9, you will see 40 microfarad if it's X5R, which is class 2, class 3. Okay, and so you build the circuit, you assume that the control loop is fixed, it has enough phase margin with 100 microfarad capacitance, but in reality, the loop is not working and oscillating, and the reason is you have a voltage across the caps that's very close to its max, and it's multi-layer ceramic capacitor, so its capacitance changes with the voltage applied. On the other hand, for aluminum electrolytic capacitor, as you can see here, there is minimum change in the equivalent capacitance of aluminum electrolytic capacitor, and that's why a lot of in some designs, some specific design, we prefer to use aluminum electrolytic capacitors over multi-layer ceramic capacitors, although multi-layer ceramic capacitors are smaller in size and cheaper in price. And as I mentioned before, any capacitor has also rating, maximum voltage and RMS current rating. Maximum voltage obviously will be the maximum voltage output voltage that the buck converter is going to generate. As for the RMS current rating, well, we said that the current in the capacitor is triangular with a peak-to-peak value that's equal to the inductor peak-to-peak current. And so basically, its RMS current will be given by this expression. Remember, I think at the very beginning when we talked about the inductor, the RMS current is the RMS value of the inductor square is equal to I out square plus one third of DIL over 2 square, right? And so since this represents the harmonic components in the inductor current, so basically its RMS value will be 1 over square root 3 delta IL over 2. And then you want to make sure that this value is less than the RMS current rating that causes 40 degree C temperature rise in the capacitor.